This is content of part 8a. If you're interested only in specific part of this video, just jump to its start time. Next, I will talk about the magnetization reversal by an electrical current or gate voltage. I will show you that demonstrated modulation of anisotropy field or offset field by electrical current or gate voltage can be used for the magnetization reversal. It is important because this mechanism can be used as an effective recording mechanism for magnetic random access memory, or MRAM in short. The magnetization has two equilibrium stable directions, for example, up and down direction. The process of how the magnetization is reversed from one to another state defines the effectiveness of the recording mechanism for the memory. Anisotropy field is roughly the magnetic field which holds the magnetization along its stable direction, also called the magnetic axis. The measurement, which I have described in previous video, clearly shows that anisotropy field can be changed by electrical current flowing through the nanomagnet or by gate voltage applied at interface of the nanomagnet. That is measured anisotropy field versus external magnetic field. Different line color correspond to measurement at different current, and you can see anisotropy field is clearly modulated by current. Additionally, the measurement has indicated that there is an additional magnetic field which is created by electrical current and which direction is perpendicular to the magnetic axis. We call this magnetic field as offset field. Similarly to anisotropy field, the offset field is substantially modulated by current. Again, this is measurement of two in-plane components of offset field, and again, line of different color correspond to different current, and you can see offset field is substantially modulated by current. Even so, the current modulation of anisotropy field and offset field is very obvious from the measurement. The modulation is too small to reverse the magnetization. The modulation of about 1% of anisotropy field definitely does not lead to the magnetization reversal. Similarly, offset field of about 200 Gauss is still small and cannot reverse the magnetization either. Having said that, I want to emphasize that the Bohr effect can be used for effective magnetization reversal. Even so, this current-induced and gate voltage-induced changes are small. They can be used in the resonance type of magnetization reversal and therefore for data recording. All the magic is due to the parametric mechanism of magnetization reversal. Next, I will shortly explain the mechanism of parametric magnetization reversal. This animation shows the main idea behind the parametric mechanism for magnetization reversal. The grip ball is a magnetization. A weak external magnetic field, Ha.08a, is applied perpendicular to the magnetization. As I have explained a minute ago, a relatively strong magnetic field holds the magnetization along its axis. This magnetic field, which is often called the intrinsic magnetic field, is rather strong and may exceed 100 or 1,000 times over this small external magnetic field Ha.08a. As a result, the weak magnetic field only slightly tilts the magnetization from its equilibrium direction, without any chance for magnetization reversal. However, when the external field is modulated so its phase and frequency matches to the magnetization precession, even a tiny field as Ha.08a is able to reverse the magnetization. It is the main idea beyond the parametric magnetization reversal mechanism. You can see from this animation that each oscillation period, the magnetization precession axis slightly turns consequently to the right and to the left with respect to the magnetic axis. As a result, the precession angle increases each period. Even though the increase might be small, it is accumulated very quickly and the precession angle becomes large until the magnetization reversal. So this is internal magnetic field directed along axis, and that is a small modulated magnetic field as Ha.08a. One difficult and tricky requirement for the parametric resonance is necessity of a constant adjustment of phase of magnetic field Ha.08a to the phase of magnetization precession. It can be done by a positive feedback loop, about which I will talk in the later part of this video. Now, I would like to explain the merits of the parametric mechanism of the magnetization reversal over the conventional mechanism of the spin transfer torque. The spin transfer torque works as follows. When the spin polarized electrons, which are shown as small balls, are injected into the nanomagnet, the magnetization of the total spin of localized electrons in nanomagnet turns into the same direction as the spin direction of the injected electrons. The magnetization of the nanomagnet is shown as a large ball. The magnetization direction of memory cell or the direction of the large ball can be changed by changing the direction of current. Therefore, the data encoded into the current can be recorded into the memory. This recording mechanism is used in both the 2-terminal and 3-terminal magnetic random access memory, or MRAM in short. In both designs, there is a pin layer, the magnetization direction of which is formally fixed, and free layer, which magnetization can be reversed. The recording principle in this memory is as follows. When this voltage is applied, a current of spin-polarized electrons flows from the pin layer to the free layer, or along the interface of pin layer, and the spin-polarized electrons are injected into the free layer. Under the spin injection, the magnetization is turned along the spin of injected electrons, and therefore according to the current direction. So the data encoded into the current is memorized by magnetization direction of free layer. The spin-transfer torque can be described by classical method using the Landau-Lifshitz equations and different types of classical torque. However, the spin is a quantum mechanical object, and its dynamic has to be described quantum mechanically based on quantum states and the electron transition between them. Even it is more than that. Since the spin describes the breaking of time inversal symmetry for electron, the restriction and the symmetry for possible breaking should be taken into account. The classic description of the spin dynamic using Landau-Lifshitz equations only mimics the quantum mechanical mechanisms. Sometimes such a description is very successful. However, sometimes it leads to a very incorrect description. For example, recently a new torque which is called the field-like torque was introduced. For the classical description, such torque is fine and possible. However, from the quantum mechanical description, such a torque severely violates some of the fundamental laws of physics. I will talk about it in the next video. Often it is okay to use a simplified classical mechanical description which is based on Landau-Lifshitz equations. However, when doing so, it should be well justified by quantum mechanical description. I will start from the quantum mechanical description of the spin transfer torque. In the later part of the video, I will show how the quantum mechanical dynamics can be described by the Landau-Lifshitz equations. I will describe the spin transfer torque in the simplest case which satisfies these conditions. The first condition is that there is a large exchange interaction between spins which keeps the spin aligned in one direction and which does not allow any misalignment between individual spin of localized electrons. Additionally, all the spins are aligned in one direction all the time, therefore all the spins are rotated without any misalignment. Another condition is that there is no magnetic domains, therefore even most distant spins are perfectly aligned. All these three conditions can be counted as one. Under this condition, the total spin of all localized electrons in nanomagnet can be considered as one subject. A reversal under these conditions is called the single domain reversal. Such a reversal occurs in the smallest nanomagnet. For the iron boron, the diameter of the nanomagnet should be 50 nanometers or less. The reversal in a larger nanomagnet is slightly more complex, but very similar. Instead of the whole nanomagnet, the coherent reversal occurs only in part of the nanomagnet, which is called the nucleation domain. The nucleation domain is unstable. A moment after creation, it's rapidly expanding over the whole nanomagnet. It is not so difficult to measure size of nucleation domain by method number 3 here, about which I will talk in another video, or you can read about it here, for example. The following is a slightly simplified quantum description of the spin transfer torque. In a ferromagnetic nanomagnet, all spin of localized electrons are coupled to each other by the exchange interactions, as it can be represented by the total spin, shown as light green ball here. There is an intrinsic field in nanomagnets, shown by the blue arrow. As I explained earlier, the intrinsic magnetic field in nanomagnet is directed along the magnetic z-axis. In equilibrium, all the spin are at lower energy level, which correspond to the state when all spin are parallel to intrinsic magnetic field. Obviously, the total spin is parallel to the intrinsic field as well. There is the upper energy level which correspond to the spins that are aligned opposite to the intrinsic magnetic field. The energy difference between these two energy levels correspond to the frequency of ferromagnetic resonance, or the FMR frequency in short. When there is a spin injection of the opposite spins, some states of upper energy level become partially occupied. It results in spin precession of the total spin, shown as a big light green ball. The angle of the spin precession increases as the number of spin down electrons increases until the magnetization reversal. The correspondence between spin precession and the simultaneous occupancy of the spin up spin down energy levels is a general feature of the breaking of the time inverse symmetry. I would like to explain this very important point. The simultaneous existence of spin up and spin down electrons does not mean literally that the spin of one electron is up and the spin of nearby neighbor electron is down. As I explained earlier, all the spin are perfectly aligned in one direction of the total spin, which is shown as this big ball. The spin up and spin down electrons, which are shown as the small balls, are only spin down and spin up projection or components of this total spin. It is similar to a 3D geometric vector which has 3 components, x, y, and z. When one component, for example this x component, changes, the direction and the length of the vector change, but the vector still remains a vector, meaning it is still pointing in one direction. It is similar to the spin. The spin has not 3 but 2 projections, for example spin up and spin down. When all the spin projection is up, the direction of the total spin is up. When the all spin projection is down, the direction of the total spin is down. When there are both the spin up and spin down components, there is a precession of the total spin. It means the spin has 3 equally natural states, or so-called eigenstates. The first state is spin up or along magnetic field. The second state is spin down or opposite to the magnetic field. And the third state is the spin precession. The spin precession is not created by any torque. It's a natural state of the spin, or more generally, a state of broken time inverse symmetry. If it would be possible to cut off all external interaction, the precession would continue forever at the same precession angle. The precession angle is directly related to the ratio of spin up and spin down electrons. It can be calculated using spinor. You can find details about the spin and relation of all spin properties to the breaking time inverse symmetry in this web page, and also including this spinor's calculations, dumping, many stuffs. Above explanation is the simplest explanation of the mechanism of the magnetization reversal by spin transfer torque. In reality, the mechanism is more complex because some parameters are changing during the spin injection, and the change of those parameters has to be taken into account. The first very important parameter which changes during the spin injection and which is important to count is the intrinsic magnetic field, shown by this blue arrow. In a ferromagnetic nanomagnet, the intrinsic field is created by the total spin of all electrons in the nanomagnet, or by magnetization. When the spin-polarized electron whose spins are opposite to equilibrium direction of the spins in nanomagnet are injected into the nanomagnet, the total spin of all electrons decreases. The total spin is the sum of all spins in a system. Obviously, when the electron whose spin direction is opposite to direction of already existed spin are injected and added to the total spin is reduced. The intrinsic magnetic field is proportional to the total spin, or to the magnetization. Following the reduction of the magnetization under spin injection, the intrinsic field is reduced as well. The energy gap, or Zeeman splitting, is proportional to the intrinsic field. And as the intrinsic field decreases, the energy gap decreases, resulting in decrease of precession frequency or the FMR frequency. The precession damping describes the electron transition from upper to lower energy level. Since the probability of electron transition between two energy levels becomes smaller when the gap between the levels becomes smaller, the precession damping decreases under the spin injection. When the number of ejected spin-down electrons becomes equal to the number of spin-up electrons, the intrinsic magnetic field becomes zero. Under further spin-down injection, the direction of intrinsic field is reversed. That event can be assigned as a moment of irreversible magnetization reversal. In the case, if the injection is stopped before this moment, when the spin-down energy level is still higher, the spin relaxation returns the magnetization into its initial spin-up stable state. Spin up. However, if the injection is stopped after this moment, when the spin-down energy level is lower than spin-up level, the spin relaxation switches the magnetization into the opposite spin-down stable state. Spin down. All electrons spin down. The requirement of an equal number of spin-up and spin-down electrons for the irreversible magnetization reversal is rather strict and cannot be broken because it is defined by the conservation of the direction of the broken time inverse symmetry. This conservation law is very fundamental and cannot be broken under any circumstances. However, the temperature can help. When the gap between energy levels is small, a tiny thermal fluctuation may excite some electrons from the lower to the upper energy level and help to reach the required balance for the irreversible magnetization reversal. Such a process is called the thermal-resistant magnetization reversal. Its effectiveness is determined by the number of electrons required to be excited to the upper energy level. The required number of excited electrons is defined by the size of the nucleation domain, about which I have talked shortly before. Next, I would like to compare two mechanisms for magnetization reversal: the spin transfer torque versus the parametric reversal. In both cases, it's necessary to inject a rather large amount of spins into nanomagnet for magnetization reversal. The amount of spin-down localized electrons should be about equal to the number of spin-up electrons. It is unavoidable for both mechanisms of magnetization reversal due to the limitation of the broken time inverse symmetry. The required number is relatively large but reasonable. A very rough estimation could be as follows. It can be assumed that there is one spin of localized electrons per atom. As I explained earlier, at first the magnetization reversal occurs in small volume of nucleation domain, which for example could be about 1 nanometer per 30 nanometers per 30 nanometers. When there is one atom in volume of 1 cubic Armstrong, it is about 100,000 spin of localized electrons in the nucleation domain. Depending on nanomagnet geometry, this is minimum number of spin which is necessary for magnetization reversal. It's still a lot, but the number is rather realistic. The problem is that a lot of spins are lost until the spin reaches the destination. It is a problem for both mechanisms, but the parametric mechanism is more effective for the spin delivery. The spin delivery is more difficult and problematic for the mechanism of the spin transfer torque. In this case, the spin should be delivered from one nanomagnet to another nanomagnet. It is a long way with many obstacles. The spin should pass the tunnel barrier, where there is a spin tunneling problem. Additionally, the spin should flow through the bulk of each nanomagnet. The transport of a large amount of spin through the bulk of a metal is not as effective, and many spins could be lost. Finally, the direction of the spin polarization of conduction electrons should be reversed, which requires many spins. In contrast, the spin path for the parametric reversal is much simpler. The spins are accumulated very locally at nanomagnet interface. There is no need for any spin transport. These accumulated spins are transferred into the spins of localized electrons parametrically, either by modulation of spin-orbit interaction or by creating local magnetic field. Neither spin transport nor the spin tunneling is required. As a result, the unwanted loss of spins are substantially smaller for the parametric mechanism. It makes the parametric mechanism to be much more effective. If you are interested to see the content and other parts of this video, you can find the links below this video.